Hi guys. So we have had a change of venue with the latest updates on the coronavirus. We've now moved to my kitchen. So I can honestly say I never thought I'd be teaching here. So in this video, we're going to start talking about capacitance a little bit more, and we're going to go through and kind of unwind the idea over a couple videos. In this video, the focus is going to be to see how to rearrange and come up with how to combine the formula or the values of capacitance for several capacitors into one overall number. So this is similar to what we did in Physics 1 when we had springs and then we had multiple springs, and we learned how if the springs were in parallel or in series, you could come up with formulas for the effective spring constant. It's basically the same. So we'll run through the logic because it's pretty much always the same logic when you're finding equivalent quantities. All right, so let's go back to the definition. Remember that Q equals C times V. And that's going to be true no matter what. And the trick is that in different situations, either the charges will add or the voltages will add, the potential drops will add. And in either case, the way to determine the effective capacitance or the equivalent capacitance is to figure out the quantity which adds, put that in the numerator, and divide that quantity by the thing which is constant. So we're going to have capacitors in parallel and in series. So let's start with parallel. So capacitors in parallel would look something like this. You would have maybe a wire going in, splitting, and then you have capacitor, and then you would have a wire going out over to some other place. And what you could imagine is that you have capacitance C1 and C2, just two numbers. They could be arbitrary. And furthermore, we could imagine maybe it's hooked up to a battery or some other component. But what we know, or what we can assume, is that the difference in voltage between the two capacitors is some amount. All right? So think about what would happen. Before you apply this voltage, or anything really, you could imagine that there was no charge on the capacitors. And then when there's a voltage applied across these capacitors, they each develop charge. Basically, on one side, they sort of draw negative charge out of the rest of the circuit. And then if you build up a bunch of negative charge on one side, it's going to pull positive, or it's actually going to push negative charge on down the circuit, leaving a layer of positive charges there. So you're going to end up with Q and minus Q, sorry, I guess minus Q and Q on the two sides. Now, notice, because these are connected with wires, and there's no potential change along wire, any wire, that means that from the top point to the bottom point, there's no drop in voltage, no change in voltage. Similarly, on the right, there could be no drop in voltage here. So if these 2 points have the same voltage, and these 2 points have the same voltage, that means that the voltage drop across one capacitor is the same as the voltage drop across the other capacitor. On the other hand, mentally, if you were to sort of, I don't know, shrink wrap this whole thing, what you would find is that the total charge on the pair would simply be the sum of the charges on the individuals. So we've learned, or with that observation, we see that if I wanted to kind of replace this pair of capacitors in parallel with one overall effective capacitor, then you should do that, and that effective capacitor would have a charge which is the sum of the individual charges, but it would have the same voltage drop as either of the two. So what we would do is we would want to, well, what was the rule of thumb? I said, find the quantity which adds and divide it by the quantity which is the same. In this case, the quantity which adds is the charge, and the quantity which is the same is the voltage. So we would want to say Q total over the voltage would equal Q1 over the voltage plus Q2 over the voltage. Now, the ratio of the total charge to the total voltage drop is nothing other than the effective or equivalent capacitance. So we say the capacitance in parallel equivalent equals, well, this ratio would be nothing other than C1, and this ratio would be C2. So that we find, in fact, in parallel, that capacitance will always add. So if you put capacitors in parallel, it's like you make them into just a large supercapacitor, which just means you can hold more and more charge per volt applied. All right, so that's for parallel capacitors. We want to do the same thing for capacitors in series. So in series, the capacitors will look something like this. Okay, so we have two capacitors, and we'll label them with a capacitance C1 and C2. And initially, you should imagine everything starts out neutral. And then a voltage is applied across the whole thing. Now, what you have to remember is that changes in potential are kind of like changes in potential energy. So if I start with a marker here, and then I drop it down a little bit and a little bit more, the total change of potential energy is just the sum. And the same exact relationship is going to be true for electric potential. So what that means is that the total drop or change in electric potential across the pair is simply the sum along the path which crosses the capacitors. Just like the potential energy of a marker being the same, or being the total potential energy drop is just the sum of the separate steps. All right, so that means that the total voltage drop is the sum of the voltage drops in a series. And that's always true. It really has nothing to do with capacitors. It's just anytime in series, you want to add the voltage drops, whereas in parallel, they have the same voltage drops. Now, let's imagine what happens. As you build up, say we hook up this to a battery, and let's say it starts out neutral, and you're going to get a little bit of charge here on the left. And then, because this little bit of metal would be neutral, but because there is a charge Q here, it's going to draw and pull out of that metal a charge minus Q right here. But since the segment was neutral, if you have minus Q over here, you're going to end up with a plus Q on the other side. And then finally on the far right, then it would draw minus Q from the right. So the end result is that if you start with neutral capacitors and you charge them up, as I've described, both capacitors have the same charge when all is said and done. So to figure out the equivalent capacitance for series capacitors, we follow the same rule of thumb. Figure out what is the quantity which adds and divide it by the quantity which is the same. Now, if I were to sort of shrink wrap this, view it as one giant capacitor, that giant capacitor would have on one side charge Q and on the other side charge minus Q. So charges are the same for the total capacitor or the individual pieces in series, and the voltage drop for the total capacitor is the sum of the voltage drops for the individual capacitors. So we would want to say the voltage drop total divided by Q equals the voltage drop for 1 divided by Q plus the voltage drop for 2 divided by Q. And remember, Q equals C times V. Rearranging that, we learn that 1 over C equivalent in series equals 1 over C1 plus 1 over C2. So capacitors in parallel have a capacitance which adds. Capacitors in series have a capacitance where the reciprocals add. And I can just tell you, maybe you can already guess what a common mistake is. Many people remember the basic formula, and they know they need to do 1 over C1 and 1 over C2. They forget to do the last flip to get C equivalent. So let's do a couple simple examples, and you'll see how this plays out. All right, so let's imagine we have two capacitors. We're going to say, let's say we have capacitors in parallel. So let's say I have C1 equals 1 farad and C2 equals 2 farads. So if I put them in parallel, C1 and C2, well, the formula for capacitors in parallel tells me I simply add these two results. So I just find that C equivalent is C1 plus C2 equals 3 farads. Okay, so that was pretty simple. Let's do a more complicated example. Let's keep the same two capacitors, and then let's add them in series. So this would say C1, C2, okay? And then I would say, all right, 1 over C equivalent equals 1 over C1 plus 1 over C2. Plugging my numbers, I see that that is 1 plus a half, so that's going to be 3 halves, and then there's a 1 over farads down there. Now, to find C equivalent, I have to flip it one last time. That's the part that people forget. Okay, now what do we notice? You had these capacitors. When we put them in series, when we put them in parallel, the capacitance is just add. That was pretty simple. But when we put them in series, in fact, the final result has a smaller capacitance. And that's true. That's what happens when you add reciprocals. The output for several ends up being smaller than what you would have had for just one. Let's do one last example. I'm going to have two more. So I'm going to have C3 equals 3 farads. I'm going to have C4 equals 4 farads. And I'm going to build a more complicated circuit. So let's imagine I had a capacitor. We'll say that this is C1. And then we're going to have capacitors. You know what, just to make the arithmetic a little bit simpler, why don't I put C3 here and C1 here, and then here we'll put C2, and over here we'll put C4. Well, now this is more complicated. I have 4 capacitors. It's neither in parallel nor series. However, you can break it down. So you can use the equivalent capacitance to smush these together. That's in parallel, so you simply add the answers. And then use the series formula to smush the result all together to get one total equivalent capacitance. So let's see that play out. This part is going to give me, so this was 3 and this is 1, so I add them together because in parallel I just add the capacitances, and this is like a single 4 farad capacitor. And then this is like a 2 farad capacitor, and this is a 4 farad capacitor. So I've effectively smushed these together to get 4. Now I want to use the formula for series on the resulting combination and add those. So that tells me 1 over C equivalent equals 1 over 2 farads plus 1 over 4 farads plus 1 over 4 farads, which equals, well, a fourth and a fourth is a half and a half is a 1, so that's going to equal 1 over 1 farad. Take the reciprocal, it'll give you the same. So this is 1 over 1 farads, and I find that C equivalent equals 1 farad. Okay? So, and that's really archetypical of how you would, it's just a very typical kind of problem where you just break it into pieces. Each little bit is separately in parallel or in series, and then you can just kind of smoosh them together using our formula for equivalence, the equivalent capacitors. Okay, let's stop there.